Does it work from here or yeah? Oh, okay. Yes.
Okay, so thanks for coming. Basically, it's time. Talking about aggregation methods in network data.
Okay. Thanks. Should I leave it open, the door, or? Oh. Okay. I know maybe most of you don't know what both of these things mean, but it's okay. We will go through that. So what is network meta-analysis? Network meta-analysis is a statistical technique used in for pharmaceutical treatments that can be extended to other fields, where basically we have a network of treatments, so made where treatments are the nodes connected by many trials. So we are trying to study, to put it all together, many treatment estimates that come from different trials for a global estimate. So trials, I mean, what is an estimate for trials? Trials can have many features, like treatments can have many features, like treatment efficacy, mortality, many side effects. So we have a different network for each outcome. And the goal of NMA is for each outcome to get a total estimate for each treatment about how strong they are. Okay.
Say what made the trial is. I'm not sure.
Okay, sorry. Okay. A medical trial is, I mean, a controlled environment where pharmaceutical companies or doctors have a controlled population, and they give a specific treatment to some of the population and another treatment or placebo to another part of the population, and then test the relative efficacy. This is what the medical trial is. And so basically the goal of rank aggregation, which is exactly what the name says, is to have different lists of efficacy, one for each outcome of the treatment, where again the outcomes are the treatment actual efficacy towards the disease, the side effect, and other things, to put them all together into a single ranking. So the goal here is to understand which one is the best treatment overall. Now let's go into detail about what both things are. This is a concrete example of what NMA looks like. So basically we have this network here, which is a network for 16 different treatments for schizophrenia, which are 15 antipsychotic drugs and placebo. Of course, you don't need to remember any of these names, just to say that what this is. And this is the network for overall efficacy. So how strong is the treatment? And of course, in this study, they measure more than one outcome. Oh, sorry. Okay, good. On the other side, they measure more than one outcome. So here is the overall efficacy, but we also have weight gain, prolactin increase, QTc prolongation, alt-code discontinuation, extrapyramidal effect, and sedation. It's not important what these things medically mean, but the most important things to see is that the first one is actually how while the treatment works, and the other are undesired side effects. So things that we don't want a treatment to do. And for each of them, we have a different network and a different estimate on how well the treatment works. Okay. The trials. So if I do a trial between, okay, let me look at the full names. Between risperidone and haloperidol, I get a link between the two of them. And the width is actually, in this case, the number of trials that I have. This is a meta-analysis. So we have some systematic review about different trials, and you put them all together in a network. Yeah. There are relative effects between the two. Is that clear or?
So, for example, like from SCR and Z, there are no studies that study the correlation between the two.
Yes, yeah, there are no direct studies that compare the two treatments. Yeah.
About how doctors have studied them together, but
yes,
they don't necessarily mean that they produce the same effect.
No, the link itself is the difference, the relative effects. So the difference between the two effects. Mhm. On the same in the same trial. Yeah. Of course, it's a statistical thing. So on the trial, there you do like an effect calculated on the sample that you have. Depends on the trial. If you have 3 drugs at the time, you have a triangle in the network.
The triangle, which is not a sum of 2 of 3 links.
No, I mean, mathematically, they will, of course, the 3 links will have related attributes, but they are 3 separate links.
These are not.
I mean, I don't remember where, but in this set, there are some 3-arm triad they're called when you have 3 treatments. There are some triangles there. Yeah.
It doesn't mean it can be used the 3 at the same trial.
Yeah, but it doesn't mean 3 in the same person. It means that you have. Yes, yeah, there are.
Cannot say which cases are triangles because they have been.
Yeah, because in the end, it's not relevant for the presentation because we are working already with the result of NMA to get the rank aggregation. So I mean, they exist, but it doesn't change the shape of the results that you get from NMA because NMA can take into account the fact that a trial has more than 2 treatments because you're dealing with the whole network in the end.
So this class does a trial. Treatments A, B, and C. Treatment A to 30 patients, treatment B to 50, and treatment C to 20. These 3 treatments are compared in one trial. So then there would be a link from A to B, a link from B to C, and a link from A to C. So now somebody else in New York tests treatments A, B, and F on 50 different patients. They also compare A and B. So the link is already there, right? But so but here you can't tell which link comes from the same trial or from a different trial. Right?
Yeah.
So in that we go to A, B, and F, so there will now be a link from A to F. But you don't know that is not the same trial as the one that compared B and C.
And in the trial, they give only 1 drug to each person?
Yes.
1 drug?
Yeah. I mean, if you test 2 drugs together, you're doing a different kind of scientific experiment, yeah. Okay. Then you have a separate network for each outcome. So in total, we have 7 networks of that do not have the same links necessarily. Because there may be like clinical trials that only study a specific side effect and not the whole thing. So this is the outcome of NMA for a specific effect. So you have an estimate for each treatment and an associated error. And this is all relative to placebo, which is our baseline. So placebo has no error and it's the default to 0 because it's a baseline. And these are all the values. Negative means better. So means the treatment is better than placebo. And they're already sorted, so you can see from better to worse, what is the effect of the treatments. But since you have a different network for each outcome, then you have also a different forest plot, which are this plot here, for each outcome. So you have 7 different plots like that. And as you can see, it's very difficult now, since they are very different between each other, to say which one is the best treatment overall. Also because some of them are missing in some trials, because they were not, I mean, for example, clozapine was not tested anywhere for prolactin increase, so we don't have any estimate here. Yeah.
And at the moment it means that they are better for that. So is it this treatment is causing that, or is it that treatment is good against it?
The axis is still the same. We set it for all of them that negative means that the treatment is better than the placebo. So even if, we change the orientation for that, yes. To avoid that some of them should be interpreted as positive and some of them negative. So this,
I think you may have to explain again what you mean by outcome, the different outcomes.
An outcome is something that you get out from a treatment, which can be, here is the overall effect, so you heal the disease, but other outcomes of a treatment are side effects, like the ones I mentioned before, like weight gain, sedation, and all the other. So here you can do medical studies that examine the efficacy of a treatment, or which is one of the outcomes, or maybe the side effects, which are other outcomes. So you can have a different network of NMA for each outcome you have. And in this meta-analysis here, we have 7 different outcomes with a set with 7 sets of trials that study them separately. So you get in the end 7 sets of estimates that rank a treatment from best to worst. I mean, it's not properly a rank, it's just like getting how much they are better than placebo for a specific outcome. So this is the overall effect, which is the capacity to heal the schizophrenia in this case. And these are all the others. Clear?
These side effects not counted in the overall.
No. No, overall, okay.
There are a couple of them which are worth not placebo.
Yes. Yeah, that's true, yeah. Yeah, because I mean, placebo in theory should not have side effects. So it's normal that placebo is one of the best in the term.
I think that something you don't want to have.
Yeah, exactly. Yeah, but regardless, negative is in favor of the treatment. We change the axis to have all in the same direction.
Okay, so here, like isn't this a standard test? Like you have 2 samples and you are comparing their means, and what is this different from typical statistical analysis?
Okay, the net is how we get these estimates here, because we do when you do network meta-analysis, you get the estimates by studying the network structure and each edge. I mean, here we go beyond the scope of the presentation, but since you ask, it's like, for example, if you do Bayesian NMA, which is one way to get this estimate here, you assume that these true estimates sample the edges, and then you do Bayesian inference to understand from which estimate did you get the whole network. So the network is the starting point, then you use NMA, and then you get this estimate here.
And it's not equivalent to the statistical test, right? What I don't understand is you have given a treatment to some and no treatment to others. So you have 2 samples. You can compare them directly.
But this is one trial. This is a meta-analysis. We have like 212 trials for this data set that some people studied, and then you build a network of that. So you already have relative efficacies, and each trial will give a relative efficacy that is very different from another. So they are incompatible if you just look at the result of a trial. At least they're not the same. They do not give the same results. So you do network meta-analysis to get an overall estimate between that kind of comes from the single estimate that you have from the single trials. Okay.
Yeah, it is. Yeah. Things in the population in Palma. For this population, we find A is better than B is better than C. You do the same thing in somewhere else in New York, you make it a different answer. Because population of patients is different. Like, they have a different diet, the weather is different, and whatever. Right? And you don't know, you can't just aggregate stuff. But you could put them all in the same thing and say, like, right? But that would not be valid. So you sort of, there's a sort of 2 layers of randomness that you assume that you say, there's a true effect, true biological effect, that is masked in Palma by local effects. The population is masked somewhere else. In New York by some other effects, so I include that as a noise term. And then on top of that, I have sampling, I only have finite number of patients. Then you put all that together and make a sort of Bayesian model that sort of reconstructs the underlying true effects that are not masked.
But he's not telling us how to do that.
Yeah, because this is not. Yeah.
Treatments A, B, and C. And then somebody else has compared A and F. Right? Then you can, in principle, say something about the comparison B to F. they have both been compared to A. E has been compared to A in Palma, and S has been compared to A in New York. And on different populations. But now you have a patient and you don't know whether to give an F or A. But for some reason, for that patient, F and A are the only option. What should you do? When you want to know something about the relative effect of F and A, but you can compare, you can build a path in this network that connects A with F, even though they have never been tested against each other directly. But you have to be careful in taking into account these population terms. Well, that's the idea of it.
Mhm.
It comes to actually do it.
Yeah. Okay. So at the end, you get this estimate here for each outcome here, so overall effect and all of the others. And as you can see, an important feature is that not all of them are, like for example, here two are missing. Not all of them are estimated, sorry, for all of the treatments. So like clozapine is also missing here, and there are some other holes somewhere. And so how do we do rankings? I mean, it's not convenient to just use the estimates D because they also have an error. So this will mean neglecting the error bar. So the most common measure is to use the Sucra score. The Sucra score is just the probability of a treatment I being better than a treatment J averaged over all the treatment J's. So it's the average probability of a treatment being better than any other. And this probability, so when the Sucra is 1, this means that the treatment is always the best one. When it's Sucra is 0, it means that the treatment is always the worst one. And this probability I bigger than J is, of course, this is done separately for each outcome L. And this probability can be calculated in two ways. And here, even if you can do it Bayesian NMA numerically, here we will use the analytical formula here. So basically, these are the estimates you saw in the forest plot. These are the errors. And then you just do you assume that they're Gaussian and do the probability that I is better than J, assuming that they are Gaussian. So this is a standardized Gaussian cumulative distribution function, and then you calculate this probability. And yeah, so we use this formula, then we get the probability, then we get the Sucra, and then we have this final list of Sucras here. So we have a score for each treatment and for each outcome. So in the end, you have 7 lists of scores that are the actual ranking that we are gonna aggregate. So the goal again is to get not 7 different recommendations for each for the treatments based on a single side effect or the efficacy, but to have like an overall recommendation. So what is which in the end you have 7 different types of effect, but which treatment are we going to recommend in the end? Which is the best treatment for the patient? This is the question we're going to answer. Okay. Now we're moving to what rank aggregation is and how do we do that. But since, NMA is not an immediate example of rank aggregation, I wanted to turn this presentation more interactive. So we can also do a simpler example of rank aggregation. So if you want, you can open this QR code here. And you can do in like 1 minute, it's something very quick. You will have a list of 10 movies and you put a star, you have to rate the movies from 1 to 10. So 10 is the best. And then we will run rank aggregation on this thing and see what happens. So each one of you is an outcome, is a different list. And then we will get the overall best movie in the end. Like super quick, you just put the star. No, if you haven't seen, no vote. That's like the missing elements in the, yeah. Okay. If anyone has other questions while other votes, you can do that now. Yes. Yes. Sorry. One is bad. It's like the number of stars. 10 is good. 1 is bad. Sorry. Yeah, more star is better. Yeah, because I noticed that it's like horizontal, but in the mobile is vertical. So yeah. Okay. Done. Okay, I will run the code now. So because it takes like 15 minutes, so where we end the presentation. Okay. Let me know when I can download the.
That is the first one. No? Okay, the best one.
Okay, everyone done? Can I download it? Okay. Okay, they are running. Okay, let's continue. So we will see the final aggregated score at the end of the presentation. Okay, each week we have a lot of stuff that we can prioritize and we can look for in rank aggregation. But what are the features that we're looking for in NMA? Okay, first, we do not need to aggregate just the rankings. And by ranking, I mean like first, second, third, just a position. We also need to aggregate the scores, our sucras, because we have scores and we don't want to lose that information. Second, since we have scores as input, we actually want scores as outputs. So we want that the ranking just doesn't give like first, second, third, just a position, but also gives another score. Third, we also have to we need to deal with incomplete list. And we will use this symbol here with the P if the method can deal with incomplete list, but penalizes missing elements. And we will use these emojis here to mark the next methods to see if they satisfy or not the condition. Then we need to weight the list because each outcome should have a different weight. For example, overall efficacy should be more important, and should weight more than sedation or other side effects, because it's more important to heal the disease rather than having a small side effect. Then we need to satisfy the Condorcet criterion that I will explain in the next slide. And then the method should be as computationally easy as possible. And this just means that if there is this label here in the future methods, it means that you can only use rational weights. And okay, what is the Condorcet winner criterion? The Condorcet winner criterion is a criterion that states that if there is a Condorcet winner amongst the element, it should be ranked first. But what is a Condorcet winner? A Condorcet winner is an element that is first. I mean that if you see this element compared to another element J, this element is ranked higher than J in more than half of the list. So suppose in the movie example, you have Shrek. Shrek is the Condorcet winner if compared to any other movie separately, more than half of you put Shrek higher than the other movie. This is an example of Condorcet winner. It's not, I mean, it doesn't always exist, but if it exists, then the criterion states that it should be first. So method can satisfy or not this criterion, and it's an important thing because it means that if a treatment is better than any other in more than half of the list, separately, of course, this any other comparison, then it means that it should be the first one. So we want this property, but of course, there are other important properties. So let's see which methods satisfy which properties. So now we'll start listing all the methods that we will use. Let's start with Borda's method. Borda's method is the simplest one. So Borda method just basically takes all the lists or the scores, ignores the scores, just uses the positions, so first, second, third, and then assigns to each position a score which is like it's like decreasing when you go higher with the position. So if there are 16 elements in our dataset, the first element gets 16 points, the second 15, the third 14, and the last one gets 1 point. So in the end, you get all of these points, and then you just sum them. This is basically the same of doing the average, although it's more tricky. This mechanism is different than just doing the average in terms of like expression, because it's used like that in many political models. And so it gives output score. It penalizes missing elements because if an element is missing, it puts them last, so 0 points. You can do weight. You can do a weighted. You can work with weights because you can do a weighted average, and it's very computationally easy. Now we have K-many optimization criteria. These criteria are basically an optimization of distance. So you define a new metric that quantifies a distance, between two given lists. And then the goal of this method is to define a new list that minimizes these distances. That is the possible that has the possible minimal distance to all of the others. And you can use these two metrics here to quantify the distance, where I'll give you a qualitative meaning of these two. That Kendall tau, which is this one, is basically counting the number of times that two elements have a different relative ordering. So if some of you put The Godfather before Star Wars and another one put Star Wars before The Godfather in two different lists, the distance, the Kendall tau will have +1. We'll count this thing as +1 when calculating the distance between the two lists. While the Spearman-Foote rule is just the relative, is basically the difference between the ranking that the same elements has to do in two different lists. So two identical lists get 0. When you start switching elements, you get a higher number. So this method is just an optimization of a numerical optimization of one of these two distances. So actually, these are two different methods. You're penalizing missing elements because you're putting them last. This satisfies the Condorcet-Wiener criterion, and you can do a weighted. You can consider it a weighted method just if you duplicate the list. Then we have spy charts. Spy charts are a method that was created in NMA. So it works directly with the sucras, which is a huge advantage, and it's a graphic method. So basically, you define this pie chart with where each sector. So for each treatment, so this chart is just one treatment. This one here. For each treatment, you define a chart, and each sector is an outcome. And the angle is the weight. So for example, here we give most of the weight to the overall effect, and the radius is the sucra. So bigger means better treatment. And then you calculate the area. So this is just the normalized area. And the total area is the final score. And then when you have a final score, you can put them in order and you get the final ranking. So it's kind of a it's kind of an aggregated sucra because this score will also be between 0 and 1. And it's basically a squared average of the elements. So you have input scores, output scores. Missing elements are penalized because, for example, if you see this is 0 because it's amyl pride or amyl prid is not does not have any information for QT, and you can do weights as we did, and it's computationally easy. Then we have generalized p-scores. Okay, if you remember the formula for how do we calculate Pij, basically this method ignores sucra, ignores any of the lists that we got in the end, and just says, why instead of using a Gaussian for each outcome, don't we use a multivariate one? So this is not the condition of I being better than J for an outcome L, but this is now the condition of I being better than J for all the outcomes L at the same time. So now you can calculate not a sucra for outcome, but not a sucra per outcome, but an aggregated sucra just with them directly. So it accepts input scores, gives output scores, penalizing missing elements because you have just a variable, like you have like one variable less, and it's computationally easy because it's just a distribution. Then we have NMA Markov chains. Okay, here there are a lot of mathematical details that I will not explain, so I will just explain them. This one. Because if you have a missing element, there is a missing variable. So it's considering like as a uniform one. So technically you are not, I mean, you're explicitly not satisfying a condition. I mean, you technically, I mean, it's not like penalizing like you put it last, but there is a significant difference if you remove.
That out?
Yes.
Just ignore it.
Yes.
Ignore it.
Yeah. Okay. Yeah. No, but I mean, it's not like a network method like the next one where you can just, I mean, it doesn't matter if there is a link or not, because you can still do the random work. Here, it actually changes the value a lot. Maybe we can see that from the synthetic simulations. I mean, yeah, it's not you don't put it last. Yeah. Yeah, it's easier. Yeah, okay, it's the opposite, yeah. Okay. But I mean, but it still is not a good thing for the rank aggregation methods because it's like overpowering it. Then we have NMA Markov chains, where basically, okay, we go back to the NMA network, and so we have then a network of treatments, and we define the edges according to this probability here. So we define edges by doing a weighted sum of this probability here. So the edges that connect I to J is the sum of the probabilities. I mean, J bigger than I, because I'm working from I to J. So I'm going from I to J if J is better. So you do the sum of all this probability to get this new set of probability here. And then once you have them, so basically you have a network, you have a random walker on this network where it's more easier for me to go from I to J if I see that all of these probability are making me go to a better node. And then you basically the aggregated score is the stationary distribution of that. So you use this. So the main concept is that you use this probability to do a random walk, and then you use the stationary probability as the aggregated score. So you're using again input scores, you're using outputs, you're getting output scores because you get the stationary probabilities. You're penalizing missing. I mean, no, sorry. You can deal without penalizing missing elements. This is like this is the first one that can do that between the one that we showed. Yeah, and then you can do weights, and then you can. It's also computationally easy. So the only thing that is missing is that it doesn't satisfy the Condorcet winner criterion. Then you have another Markov chain method, the MC4. And in this method, you have again a random walker, and the stationary probability will be the aggregated score. But now the rules of the working are the following. I'm at node. Imagine that I'm node I. I pick uniformly a J. And then if this J is better than me in more than half of the list, I go to this node. If it doesn't, I resample. So I can only move to nodes that are better than me, than I mean, in this case, in more than half of the list. So we are not using sucras, we are not using input scores, we are just using relative positions, so no input score. We have output scores. We are not penalizing missing elements because, I mean, as long as the network has a sound structure, we can do the random walk. You can use weighted list, and it's computationally easy. And now we have this another graph-based method, although the formula looks quite, I mean, not complicated, but like that. I mean, it's actually quite easy because now you define a network where you can have multiple edges between the same nodes, and you put an edge for each list where I is better than J. So you check for a node I, so if, for example, you ranked Harry Potter better than The Godfather 5 times, you have 5. You have this value here. So you have this directed network here, and then you calculate the ratio between the in degree and the out degree. This is it. This is the aggregated score. So, and the +1 is just to avoid division by 0. So you have an output score, but not an input because you're not using the sucre. We're just using the times that something is better than the other. You're not penalizing missing elements because you're working with a network. You can do weights, just putting weights instead of 1, and then it's computationally easy. And then we have the last one, which is Bayesian inference. Bayesian inference, we now assume, okay, we assume that all of the outcomes, all of the rankings that we have, all of the scores come from a list of true scores. So we assume that these true scores, if you do, I mean, basically the scores that we see are sampled Gaussianly from these true scores. So, for example, we're assuming that the true ranking of Star Wars is 8, so that all the ratings that you put are Gaussian samples from this 8. And the goal of, and then we do Bayesian inference to calculate these true scores here. And for sucra, of course, we need to truncate the distribution because sucra is from 0 to 1. But this is the method. So this is actually one of the best ones in terms of effect because it uses input scores, returns output scores, also that are similar to the input one. If we do not penalize missing elements, we can do weights, and it also satisfies the Condorcet criterion. The problem is that it's very computationally expensive because it's super slow compared to the other. And this is basically this is the table with all the properties that we mentioned because I'm pretty sure that most of you forgot all of them. me included, maybe. So this is the list of the properties. As you can see, Bayesian inference and Markov chain from NMA are the one that have almost all of them. And this is the take-home message from the list of methods that I made. So now let's see the result of applying these methods to the antipsychotic dataset of before. Since there is no universal way to assess which method is better than the other, we will just use Pearson correlation between the scores. So original scores versus aggregated scores, and see how similar are these lists between each other. And we also use Spearman correlation, which is Pearson, but we use the ranking and not the scores. So instead of using the sucras, we use just the position in the list. And missing elements will be placed at last during this thing, because this is what the methods do when they have missing elements in most of the cases. Okay, this is the correlation between the original list. Here, no rank aggregation was made. This is the correlation between the different outcomes. So these are the outcomes. This upper triangle is the Pearson correlation, and the lower triangle is the Spearman correlation. So let's focus on the upper one. I think that the most important feature of this thing, so the thing that you should remember for the other plots, is that the overall efficacy is anti-correlated with most of the outcomes, excluding AD, which is all-cause discontinuity, which basically means I'm quitting the treatment. So it means that most of the times a treatment that has a higher efficacy will have stronger side effects in a negative way. So this will be very clear when we see the next plots about how rank aggregation methods aggregated the score, because basically the thing is that whenever they try to match with the overall efficacy, which is the most important thing, they will not match with many of the other outcomes. This is the method-method correlation. So this is the correlation between the aggregated ranking, each one made with a different method. And again, upper triangle is Pearson, lower triangle is Spearman, and this is the no weight scenario. So all of the outcomes have the same weight here. And as we can see, they're almost all identical. I mean, they are very, very high values, and the only method that is very different from the other are generalized p-scores. So all the other have very high value of correlation, but generalized p-scores gives a very different list. Why? Because generalized p-scores, when we do a multivariate analysis, it needs to use correlations. It needs to assume some correlation between the variables in the multivariate distribution. Correlation that we don't have because we didn't do the original NMA on this study, because of course this NMA has been done on a paper that doesn't publish the whole set. I mean the whole set of intermediate results. So we did an assumption with the final results that apparently are not good enough to assume this correlation. So we will need the total set of original data to make this method work like 100% correctly and be competitive with the others. Here we have, okay, since we don't have much time, let's just look at the Pearson correlations. Here we have the Pearson correlation between the aggregated ranking and the original outcomes. So these are the original outcomes. This AVE is like average of this thing. So this value here is the average of the row. So in general, we wanted the aggregated ranking on average to be similar to the ones that we are aggregating. And we can see that all of them have quite similar values, but the lowest one are generalized p-score for the reason that I said before, and Markov chains for, which apparently doesn't work well with as the others, because most of the others use sucra, while MC4, if you remember, doesn't use sucra, just use relative order. So apparently using relative ordering for this method is not enough, and so it's not competitive with the others. And now we put weight. So now we see that now we go to the scenario where the overall effect has most of the weight. This is actually the pie chart you saw at the beginning is from this outcome, from this scenario here. So we have that 50% of the weight is given to overall effect, and the others have equal weights distributed uniformly. This is similar to the one before, but the real difference is when we go to the method outcome Pearson correlation, because now they are, of course, more similar to the overall effect because we gave it most of the weights, excluding generalized p-scores that is still failing. But it's also similar to AD because as we saw before, it was correlated with the overall effect. And the only one that is not, that doesn't really survive again is Markov chains. But if we go to the Spearman, Markov chain is competitive because Markov chains only uses positions and Spearman is the ranking between the correlation between the ranking. So the correlation between the positions. So since we care more about the actual scores because we work with Sucras and we want more detailed scores, Markov chains are not a good method for that. And generalized p-scores, we will need a better data set to maybe it will show off. So basically, what did we find out? The generalized p-score thing that I explained, the fact that we did not notice that a method that penalized missing elements were not working good because they were working good. So in this data set here, the correlation between outcomes was a stronger feature than actual missing elements. So that means that this data set does not have a significant number of missing elements, but has significant correlations and anti-correlation between the outcomes. Also, Sucra in this dataset does not have much information because many methods that work without scores, like Borda, worked well. So it means that for this dataset here, the rankings are already fine. Sucras are not that important. Here we can have messier datasets where Sucra gets important. And then and this is actually a consequence of that. So, and also Borda is cool. Borda is like the most naive method, which is basically an average, but here worked okay. So it means that compared to the complexity of all the other methods, a simple one still works okay. So it's still nice to see that that little Borda survived. So the best picks, looking at the attribute, the features that we want in a method and the results are NMA, Markov chains, and Bayesian inference, but also these ones are good picks to use for this specific data set. And this is what aggregated rankings looks like. So this is the Bayesian inference aggregated ranking for the overall effect weights more scenario. So this is the old table, as you saw before. And this is the final ranking. And as we can see, placebo is not the last. So that means that there are treatments that when you take into account side effects, get worse than placebo. So side effects are so bad for some treatments that maybe placebo is better if some doctors or some patients would prefer to not survive these side effects. Of course, placebo is not very high, hopefully. Medicine would be very, low quality if that was true. But yeah. So that's it. This is again, a reminder for the table, which is the take-home message. So do you have any questions, or this is the thing? Now, yeah, we can see the movie thing. Okay, let's see if the Bayesian one is over. No? Okay, wait, because okay, it's almost over. Okay, let's see, let's go one by one. Okay, this is Borda. Wow, interesting list. So this is Borda. Since you are 11, I think 11 people voted, the highest possible score was 110. So Shrek got a quite high score. So Shrek, Lord of the Rings, Godfather is the top 3. Then we have MC4, which has the same order, but Twilight is third, while in the previous one, Twilight was last. And this is because here we are, actually, no, this is none of them. These two methods are not looking at the scores. They're just looking at the ordering. But now we have, again, this one, according to the graph-based method, Lord of the Rings is first and Shrek is third. And now we have the optimization that stays, the Shrek is first one. The other optimization that is, almost the same. Then we have spy charts where we can actually see a spy chart for each movie. So this is The Dark Knight, The Godfather, Star Wars, the Lord of the Rings, the Matrix. So there is only one person that hasn't seen the Matrix. Harry Potter, Back to the Future, quite unpopular, and Shrek. Okay, exploded. And then wow, nobody has watched Twilight. So for example, we saw that MC4 that does not penalize missing elements gave a higher score to Twilight because there are a lot of missing elements, while the method that do penalize that give it a lower score. And then High School Musical, and this is the final score list. So Twilight, of course, nobody has seen it, so low. Then we have the Bayesian one, which is not over. Sorry. I think it will be over in, I don't know. Usually this is something like 5 to 10 minutes, but so yeah. Yeah.
Maybe a short and curious question. You mentioned the methods only accept rational weights.
Yeah.
Do you want to use other different, or I don't know?
No, I mean, because usually with weights you can put any number you want, but most of the a few methods do not have you cannot put a weight, but putting a weight means duplicating the list for some of the methods. So duplicating the list means that you can only use rational weights because you can duplicate some of them to make a rational weight. So if you want something 2/3, then you duplicate one and the other stays the same, and you can play with like that. Yes, basically you put integer weights, but you can, yeah.
There are methods to combine, or the other methods to combine ranks.
All of these methods. Yeah, all of these methods, I mean, in NMA, the only one that exists are the NMA Markov chain, the generalized p-scores, and spy charts. All the others are from different fields. Most of them from web search things, so because they can see how many people reacted to different pages. Some of them are from rating customer services, like movie platforms too. So I mean, none of the method is like original here. The original part is to transform them to apply them to NMA because a few of them were unsuitable in the original form. Like for example, the Bayesian one is more like a generic framework, and then you have to adapt it for the NMA distributions. Yeah, and sorry, I think we will not be able to see it. Okay. No, so thanks. Maybe I will send it later. Okay. Thanks. Yeah, okay. This audio, okay, off.